Black body radiation and the UV catastrophe. Here we're starting to talk about quantum mechanics a bit. Quantum mechanics is very mathematically intensive. We're not going to get into the heavy math of it, but we do want to understand the concepts of it and how it applies to chemistry, making molecules and how atoms behave and such. A little background, I guess. Classical mechanics, what physicists and chemists have talked about for hundreds of years, deals with how the laws of how matter and energy behave on the large macroscopic world where you and I live, where you and I exist. So the ball rolling down the hill, that kind of a thing. We're very large compared to the atoms and the molecules and the electrons that make us up. So this is the macroscopic world. The microscopic world, on the other hand, down when you get down to the size of an atom and of a molecule and of an electron, things behave a little differently down there, and that's because the nature and the property of matter at that small a scale is different than what we see on the macroscopic, where it's made up of millions and millions and millions of these atoms put together. All right, and so how these bodies behave, how matter behaves, what they look like, and the laws that govern them are different, and it took scientists a while to figure that all out. Black body radiation and the UV catastrophe was maybe the first hint, the first experiment, and the first explanation that started to get at the microscopic world where things are quantized. Some things are quantized anyway. Here's how it goes. Black body radiation, all matter, when you heat it up, emits light. You and I know that. You got a bonfire, you got some glowing coals or glowing wood at the end of it. Why are they glowing? Why are they emitting this red or orangish light? That's because they're hot. You know, you heat up steel, it starts glowing that red color too. Why? Because it's plenty hot. You got to get it nice and hot, but when you do, they start emitting this this light, this red light. And actually, if you get it even hotter, it starts getting more greenish, and then more yellowish, or yellowish first, I guess, and then greenish and bluish, and finally, if you mix all those colors together, you get white light coming off of it. And that's kind of what's happening with the sun. It's so darn hot out there, you get all the colors coming off, and it looks like white light to us. It's all the colors combined. All right, and so this is called black body radiation, and trying to understand it, trying to explain it, like I said, led to the first ideas of quantum mechanics. Now here on this table from the textbook, we have different temperatures from 3 up to 6,000 Kelvin. So again, that's pretty darn hot. And where they emit light and what wavelengths. So at 3,000 degrees, for example, you see they're emitting it maximally at about maybe 3.2 micrometers. That's not to say they're not emitting it down here at smaller wavelengths or up here at much larger ones, but it peaks. It peaks at that. And then you get up 4,000 degrees, so make it hotter yet. Notice that we've got this broad spectrum, but this time it's peaking now a little lower, more like maybe 0.85 or 0.89 or something like that in the wavelength, micrometers. Right. Again, it's emitting both higher and lower, but that's where it peaks. And you see, as they get hotter and hotter, that shift, that peak, it gets bigger, of course, because it's getting hotter. It's the intensity's more light's coming off. But the peak of the maximum where it's coming off is shifting to lower wavelengths. Now, it doesn't shift forever and ever. It doesn't just go this way like a linear, but it's got this curved sort of a path, this dotted line in the figure, and it goes up. When you get up to about 6,000 degrees, now the peak is right there, right in the middle of the visible spectrum. Right. And so this is basically the light that the sun is giving off. The sun is about 6,000 degrees Kelvin. And so these wavelengths under this blue line, all these different wavelengths are what it's giving off. Notice it doesn't give off very many way down here in the low wavelength, and not so many up here in the higher wavelength. It peaks here in the visible spectrum. And a lot of people have suggested that that's why our eyeballs actually can see in that range of wavelengths from the blues up through the reds here, because, well, that's where maximally the sun's giving off the light, and so I guess that would make sense that that's where we would want to see. But like I said, hey, it's giving off plenty of radiation, both higher and lower as well. Okay, classical mechanics, trying to apply the laws of physics as they exist in the large macro world, macroscopic world, would lead to equations and theories and predictions of this line that I've dotted in here of where the peak should be. So essentially here, we've got this idea of it peaks much faster and it goes up and it never comes back down. It just kind of goes up and up and up forever. So it doesn't show us a peak, it just shows us that that classically is where it would be. And now what about different temperatures? It wouldn't shift left right, it would just go higher and higher and higher. It'd become more intense, and it would just show that, hey, we got huge amounts that should be coming out here in the ultraviolet. Even when you drop to lower and lower temperatures, so you take my red dotted line here and you break it lower, and so maybe it would be running, well, let me draw it in here. I'll just use this highlighter, this purple highlighter. It would be way down here and it wouldn't peak very much, so it would be kind of like this, and then finally kind of start coming up, something like this, right? It's like the whole thing is just kind of shifted downward. The problem is that even at very low temperatures, such as like room temperature or body temperature where you and I are at, you've got this, in this region right here, this large amount of energy. I meant to choose yellow. There we go. There we go. This large amount of ultraviolet radiation, which should be coming out. See, according to classical theory and the classical equations, you and I should be glowing right now in ultraviolet radiation, and we're not. You look at us with we are just not doing it. We might be giving off actually a little bit infrared, but we're not glowing with the ultraviolet like we're supposed to be according to classical mechanics. You see, the real data shows that, again, it goes up and then it comes back down. It doesn't go up forever. And that's what they call the ultraviolet catastrophe. Well, Max Planck, right around the turn of the century, about 1900, Max Planck was looking at this data. He didn't really understand necessarily why and what was happening. Why did it come back down? Why did we not see the ultraviolet catastrophe? But he came up with a model that at least fit the data. And when he punched through and got his equations, they predicted the correct, it goes up and then it comes back down kind of a graph. Right? And he did this by quantizing the energies. That is to say, not making the energies completely, any energy is possible, but only certain energies are possible to be released. They're quantized. They were broken up into small pieces, in other words. Again, the idea of quantization, it's not continuous, it's quantized. I like to describe it as, say you're traveling down the road. We know that the kinetic energy is the energy of your motion. The faster you go, the higher your kinetic energy. And so if I'm going 10 miles per hour, I've got a little kinetic. If I'm going 75 miles an hour, I've got a lot of kinetic energy. And I know that I can creep that car up or down in the speed, and I can continuously go anywhere from 0 up to 75 or beyond. Anything is fair game in there. Quantized energy says, that wouldn't be possible. You can go 0, you can go maybe 15, you can go 30, you can go 37, whatever. There are certain ones that you can go, certain speeds that refer or that correspond to certain kinetic energies, but all the ones in between, for whatever reason, not allowed. You can't do it. You have to go either one, dot. They're quantized, in other words. Okay? Now, this is very much against what we see in the classical mechanical world, the large microscopic world. We don't see that. Everything's continuous for us. You throw a baseball, it can go anywhere from 0 up to 100 miles per hour, whatever. It's not stuck at, you must go 69 miles per hour. We're not quantized. Right? But Max Planck, again, used a model where he said, I can actually predict this if I quantize the energy. And it had to do with the number of modes of energy under these quantizations that were allowed at different temperatures. Again, we don't need to get into that math to understand the concept. Okay? And he came up with a very simple equation, therefore, for the energy that was allowed. And that was this guy right here, the fact that E, the energy of that light, would equal NH nu, right? Where N is the quantization constant, right? Or sometimes called a quantum number. And it was equal to 1, 2, 3, 4, just counting. 1, 2, 3, 4. H was just a proportionality constant. We now know it as Planck's constant, named after him, of course. And nu was the frequency of the light. So if you took the frequency, you multiplied it by some proportionality constant, and then quantized it, 1, 2, 3, 4, and you plug that in, he predicted the right thing. Now, H, the Planck's constant, is equal to 6.626 times 10 to the minus 34 joule seconds. Yeah, that's the unit, joules times seconds. Right? And so the frequency, red light, green light, blue light, whatever the frequency of the light, we can plug that in, and then 1, 2, 3, 4. That would give us the energy that actually was allowed to be emitted, if you will, by these black bodies. And what do you know? It worked, like I said. He didn't understand why, but it did work. So let's look at problem 6.2 as an example here of how we can use Planck's equation and Planck's constant to calculate the energy. There's a lot of figures here. We're going to have to come back to explaining all of those a little bit later. But okay, here we go. 6.2 says, when we see light from a neon sign, we are observing radiation from excited neon atoms. So these neon atoms have been warmed up, if you will. We haven't stuck them in a fire, but we've shot a lot of electricity through them. We've jacked their temperature up, and they're going to start glowing. Black body radiation. Okay. It says, if this radiation has a wavelength of 640 nanometers, what is the energy of the photon being emitted? The photon is this idea of a quantized packet of light. Right? It's a particle, if you will, of light. Although, again, light isn't necessarily a particle, but it's the idea of a packet of energy of light. Right? So we can think of it as a particle. That's not entirely wrong. It's not entirely right either. All right? A photon. So if I emit one photon, or if I emit 2 photons or 3 photons, I think of it almost like BBs coming shooting out of the gun, but they're BBs, little packets of light, and they're quantized by the amount of energy that they're carrying. Okay? And it says, calculate, well, what is the energy of one of those photons of light that are being emitted by this neon sign? Right? So how do we do that? We use Planck's constant. So let me get my pen here. If we have the idea that energy is equal to NH nu, according to Planck's constant, and I'm trying to calculate the energy for one photon, so N is going to equal 1. Actually, before I do that, let me show you as well. In H nu, because C equals lambda nu, you can always solve that for lambda and plug in. Lambda would equal C over, nu frequency would equal C over lambda. And I can take that and I can plug that in for my frequency. So energy also equals NHC over lambda. And that might be a little easier to use since they gave me lambda in this problem. Alright, so let's plug in some numbers. One photon, N equals 1. Planck's constant, 6.626 times 10 to the minus 34 joule seconds. That's a 334. And then C, speed of light, 2.998 times 10 to the 8th meters per second. Notice I'm keeping tracks of my units here. I've got a per second here and a second. I need to use consistent unit always. Meters and joules I haven't talked about yet, but I need to plug in the wavelength, and again I'm using meters over here in the speed of light, so I better plug it in meters as well. And it was 640 nanometers. Nano means times 10 to the minus 9, so 640 times 10 to the minus 9 meters. That's good because now my meters and meters will cancel as well. Alright, that should be the energy of this. Let's go over to our calculator here and plug that in. I've got 1 times 6.626 E minus 34 times C, 2.998 E8, divided by the wavelength, 640 E minus 9, equals 310.3 times 10 to the minus 21. Wow, that's really crazy small. Make sure I did that right. Yeah, 6.6 looked good to me. So that's the energy in joules of one little photon here. 310 times 10 to the minus 21 joules. Just a little teeny tiny packet of energy is coming off of that.